So here's our starter problem. We have a crate that has a mass of 12 kilograms. It's on wheels, so there's no friction. We're going to push it with 50 newtons of force through 5 meters of displacement. And it's real simple. I just want to know how much work was done on the crate by this force, and what is the final velocity of the crate. And so for part A, well, work is equal to the force times the displacement times the cosine of the angle between them. Now, I'd really like you to include this every time you write down the basic equation for work, because it's really easy to forget about. And so we know that the force here is 50 newtons, and we're pushing it through 5 meters. And the cosine of, what is the angle between this force and this displacement? 0 degrees. And the cosine of 0 degrees is 1. So this really doesn't matter. Well, I mean, it matters, but it's not changing the value of our answer. 5 times 5 is 25 plus 0, and a newton meter is a joule. So it did 250 joules. Now for part B, we're going to use kinematics this time, but later in the period, we're going to develop a new idea that's going to let us solve this problem a different way. But I want to know, what is the final velocity? Now look at what I know. I know the displacement. I know the initial velocity. I don't know the acceleration, but I can figure out the acceleration from the force and the mass. What do I not know? I don't know time, and I'm not given the time. I'm not asked for the time. So I'm going to start off with the equation. V squared equals V naught squared plus 2a delta x. And I know this force is a constant force, so the acceleration will be constant, so I can use the kinematic equations. Well, what do I know? I know the initial velocity is 0. I don't know the acceleration, but I do know delta x. So what I need to do is figure out what the acceleration is. Well, I can use a procedure for it, but I'm going to take a little bit of a shortcut. I've got gravity pulling this down. I've got a normal force compensating for that gravity, but this is really the only force that isn't being canceled out or isn't being balanced out. So this is the 50. So we know the net force equals mass times acceleration. So the acceleration is equal to that net force divided by the mass. So we know the acceleration here is 50 newtons. And we know the mass is 12 kilograms. So what is 50 divided by 12? What do we get? Is it 4.7? Oh, 4.17? Yeah, 4.16666. Yeah, so we'll just round it off. Meters per second squared. And so now we can solve. It's equal to the square root of 2a delta x. And that's 2 times the acceleration. And then times delta x is 5 meters. So with my calculator, I'm going to go 2 times 4.17 times 5 equals, and then I'm going to raise that to the power of 0.5. I got 6.46 meters per second. Now let's think of this in terms of what we were talking about the other day, in terms of energy. Some outside agent, a person or something, pushed on this thing, and they did work, which means they transferred energy into it. And now this thing is moving pretty good. 6.46 meters per second. That's pretty fast. That's like a pretty good run. Which means that, you know, if you're standing right here and someone pushes on it and this crate hits you, you know, runs into you, it's going to do, it can do something to you. It can make something happen because you gave this person or this agent, whatever, poured energy into it, and now because it has mass and because it's moving, it can do things. It has what we call kinetic energy. Okay, and what we're going to do later in the period today is we're going to develop an equation for kinetic energy. How much kinetic energy does it have? And develop this thing called the work energy theorem. So anyway, any questions on this problem? Okay. That is all.